The Internals of Postgres. Chapter 9. Write-ahead logging. WAL. A transaction log is an essential part of a database, because all database management systems are required not to lose any data even when a system failure occurs. It is a history log of all changes and actions in a database system so as to ensure that no data has been lost due to failures, such as a power failure or some other server failure that causes the server to crash. As the log contains sufficient information about each transaction executed already, the database server should be able to recover the database cluster by replaying any changes and actions in the transaction log in case of the server crash. In the field of computer science, WAL is an acronym of Write-Ahead Logging, which is a protocol or a rule to write both changes and actions into a transaction log, whereas in Postgres, WAL is an acronym for Write-Ahead Log. There, the term is used as a synonym of transaction log, and also used to refer to an implemented mechanism related to writing action to a transaction log, WAL. Though this is a little confusing, in this document, the Postgres definition has been adopted. The WAL mechanism was first implemented in version 7.1 to mitigate the impacts of server crashes. It also made possible the implementation of point-in-time recovery, PITR, and streaming replication. Although understanding of the WAL mechanism is essential for system integrations and administrations using Postgres, the complexity of this mechanism makes it impossible to summarize its description in brief. So the complete explanation of WAL in Postgres is made as follows. In the first section, the overall picture of the WAL has been provided, introducing some important concepts and keywords. In the subsequent sections, the following topics are described: the logical and physical structures of the WAL, transaction log, the internal layout of WAL data, writing of WAL data, WAL writer process, the checkpoint processing, the database recovery processing, managing WAL segment files, and continuous archiving. 9.1 Overview. Let's take a look at the overview of the WAL mechanism. To clarify the issue the WAL has been working on, the first subsection shows what happens when a crash occurs if Postgres does not implement WAL. The second subsection introduces some key concepts and shows the overview of the main subjects in this chapter: the writing of WAL data and the database recovery processing. The final subsection completes the overview of the WAL, adding one more key concept. In this section, to simplify the description, the table A, which contains one page, has been used. 9.1.1 Insertion operations without WAL. As described in Chapter 8, to provide efficient access to the relations pages, every database management system implements shared buffer pool. Assume we insert some data tuples into table A on Postgres, which does not implement the WAL feature. This situation is illustrated in figure 9.1. So 1. Issuing the first insert statement, Postgres loads table A's page from a database cluster into the in-memory shared buffer pool and inserts a tuple into the page. This page is not written into the database cluster immediately. As mentioned in Chapter 8, a modified page is generally called a dirty page. 2. Issuing the second insert statement, Postgres inserts a new tuple into the page on the buffer pool. This page has not been written into the storage yet. 3. If the operating system or Postgres server should fail for any reasons, such as a power failure, all of the inserted data would be lost. So, database without WAL is vulnerable to system failures. 9.1.2 Insertion operations and database recovery. To deal with the system failures mentioned above without compromising performance, Postgres supports the WAL. In this subsection, some keywords and key concepts, and then the writing of WAL data and recovering of the database are described. Postgres writes all modifications as history data into a persistent storage to prepare for failures. In Postgres, the history data are known as xlog records, or WAL data. Xlog records are written into the in-memory WAL buffer by the change operations, such as insertion, deletion, or commit action. They're immediately written into a WAL segment file on the storage when a transaction commits/aborts. To be precise, the writing of xlog records may occur in other cases. The details will be described in section 9.5. LSN, log sequence number, of xlog record represents the location where its record is written on the transaction log. The log sequence number of record is used as the unique ID of the xlog record. By the way, when we consider how database system recovers, there may be one question. What point does Postgres start to recover from? The answer is redo point. That is, the location to write the xlog record at the moment when the latest checkpoint is started. In fact, the database recovery processing is strongly linked to the checkpoint processing, and both of these processings are inseparable. The WAL and checkpoint process were implemented at the same time in version 7.1. As the introduction of major keywords and concepts is just finished, from now on, it will be the description of the tuple insertion with WAL. See figure 9.2. A checkpointer, a background process, periodically performs checkpointing. Whenever the checkpointer starts, it writes a xlog record called checkpoint record to the current WAL segment. This record contains the location of the latest redo point. Two. Issuing the first insert statement, Postgres loads the table A's page into the shared buffer pool, inserts a tuple into the page, and creates and writes a xlog record of this statement into the WAL buffer at the location LSN1, and updates the table A's LSN from LSN0 to LSN1. Three. As this transaction commits, Postgres creates and writes a xlog record of this commit action into the WAL buffer, and then writes and flushes all xlog records on the WAL buffer to the WAL segment file from LS1. 4. Issuing the second insert statement, Postgres inserts a new tuple into the page, creates and writes this tuple's xlog record to the WAL buffer at LSN2, and updates the table A's LSN from LS1 LSN1 to LSN2. When this statement transaction commits, Postgres operates in the same manner as step 3. 6. Imagine when the operating system failure should occur. Even though all data on the shared buffer pool are lost, all modifications of the page have been written into the WAL segment files as history data. The following instructions show how to recover our database cluster back to the state immediately before the crash. There is no need to do anything special, since Postgres will automatically enter into the recovery mode by restarting. See Figure 9.3. Postgres will sequentially read and replay xlog records within the appropriate WAL segment files from the redo point. Time 1. Postgres reads the xlog record of the first insert statement from the appropriate WAL segment file, loads the table A's page from the database cluster into the shared buffer pool. Redo point. 2. Before trying to replay the xlog record, Postgres shall compare the xlog record's LSN with the corresponding page's LSN. The reason why doing this will be described in section 9.8. The rules of replaying xlog records are shown below. If the xlog record's LSN is larger than the page's LSN, the data portion of the xlog record is to be inserted into the page, and the page's LSN is updated to the xlog record's LSN. On the other hand, if the xlog record's LSN is smaller, there is nothing to do other than to read the next WAL data. 3. Postgres replays the remaining xlog records in the same way. Postgres can recover itself in this way by replaying xlog records written in WAL segment files in chronological order. Thus, Postgres' xlog records are obviously redo log. Note: Postgres does not support undo log. Redo log. Though writing xlog records certainly costs a certain amount, it's nothing compared to writing the entire modified pages. We are sure we can get a greater benefit, i.e., the system failure tolerance, than the amount we paid. 9.1.3 Full page writes. Suppose that the table A's page data on the storage is corrupted because the operating system has failed while the background writer process has been writing the dirty pages. As xlog records cannot be replayed on the corrupted page, we would need an additional feature. Postgres supports a feature referred to as full page writes to deal with such failures. If it is enabled, Postgres writes a pair of the header data and the entire page as xlog record during the first change of each page after every checkpoint. Default is enabled. In Postgres, such a xlog record containing the entire page is referred to as backup block or full page image. Let's describe the insertion of the tuples again, but with the full page writes enabled. See Figure 9.4. 1. The checkpointer starts a checkpoint process. 2. In the insertion of the first insert statement, though Postgres operates in almost the same manner as in the previous subsection, this xlog record is the backup block of this page, i.e., it contains the page entirety. because this is the first writing of this page after the latest checkpoint. 3. As this transaction commits, Postgres operates in the same manner as described in the previous subsection. 4. In the insertion of the second insert statement, Postgres operates in the same manner as the previous subsection, since this xlog record is not a backup block. 5. When this statement's transaction commits, Postgres operates in the same manner as in the previous subsection. 6. To demonstrate the effectiveness of full page writes, here we consider the case in which the table A's page on the storage has been corrupted due to the operating system failure which occurred while the background writer has been writing it into the HDD. Restart the Postgres server to repair the broken cluster. See figure 9.5. 1. Postgres reads the xlog record of the first insert statement and loads the corrupted table A's page from the database cluster into the shared buffer pool. In this example, the xlog record is a backup block because the first xlog record of each page is always its backup block according to the writing rule of full page writes. Step 2. When a xlog record is its backup block, another rule of replaying is applied. The record's data portion, i.e. the page itself, is to be overwritten onto the page regardless of the values of both LSNs and the page's LSN updated to the xlog record's LSN. In this example, Postgres overwrites the data portion of the record to the corrupted page and updates table A's LSN to LSN1. In this way, the corrupted page is restored by its backup block. Three. Since the second xlog record is a non-backup block, Postgres operates in the same manner as the instruction in the previous subsection. Postgres can be recovered even if some data write failures have occurred. Of course, this does not apply if the file system or media failure has occurred. 9.2. Transaction log and WAL segment files. Logically, Postgres writes xlog records into the transaction log, which is a virtual file 8 bytes long, 16 exabyte. Since a transaction log capacity is effectively unlimited, and so can be said that 8-byte address space is vast enough, it is impossible for us to handle a file with the capacity of 8-byte length. So a transaction log in Postgres is divided into files of 16 megabytes by default, each of which is known as a WAL segment. Note, WAL segment file size. In version 11 or later, the size of WAL segment file can be configured using WAL segsize option when Postgres cluster is created by initdb command. Figure 9.6, transaction log and WAL segment files. The WAL segment file name is a hexadecimal 24-digit number, and the naming rule is as follows. WAL segment file name equals timeline ID plus unsigned int 32 of LSN minus 1 over 16 megabytes, 16 million, times 256 divided by, or plus unsigned integer 32 of LSN minus 1 over 16m modulus 256 Timeline ID. Postgres' WAL contains the concept of timeline ID, 4-byte unsigned integer, which is for point-in-time recovery, PITR. However, the timeline ID is fixed to 1 in this chapter because this concept is not required in the following descriptions. The first WAL segment file is long string of 0 and 1s. If the first one has been filled up with the writing of xlog records, the second one would be provided. Files of successor is used in ascending order in succession. After has been filled, the next one will be provided. In this way, whenever the last 2-digit carries over, the middle 8-digit number increases by 1. Similarly, after has been filled up, this will be provided, and so on. PG xlog file name and PG WAL file name. Using the built-in function pgxFileName version 9.6 earlier, or pgWALFileName version 10 or later, we can find the WAL segment file name that contains the specified LSN. An example is shown below. Select pgxlog file name, this. 9.3. Internal layout of WAL segment. A WAL segment is a 16 megabyte file by default, and it is internally divided into pages of 8 kilobytes. The first page has a header data defined by the structure xlog long page header data, while the headings of all other pages have the page information defined by the structure xlog page header data. Following the page header, xlog records are written in each page from the beginning in descending order. See figure 9.7. Xlog long page header data structure and xlog page header data structure are defined in source include access xlog internal.h. The explanation of both structures is omitted because those are not required in the following descriptions. The first one has long page header data. 9.4. Internal layout of xlog record. An xlog record comprises the general header portion and each associated data portion. The first subsection describes the header structure. The remaining two subsections explain the structure of data portion in version 9.4 or earlier and version 9.5 respectively. The data format has changed in version 9.5. 9.4.1 Header portion of xlog record. All xlog records have a general header portion defined by the structure xlog record. Here, the structure of 9.4 and earlier versions is shown in the following, though it is changed in version 9.5. So we have the total length of the entire record, the exact ID, total length of the RMGR data, XL info flag bits, see below, RM ID, the resource manager for this record, 2 bytes of padding here, initialized to 0, XL prev, pointer to the previous record in the log, and XL CRC of this record. Apart from two variables, most of the variables would be so obvious that they need no description. Both XLRMID and XLInfo are variables related to resource managers, which are collections of operations associated with the WAL feature, such as writing and replaying of Xlog records. The number of resource managers tends to increase with each Postgres version. Version 10 contains the following: Operation Resource Manager. Heap tuple operations, RM heap 2, index operations, RM btree, RM hash, RM gin, RM gist, RM special gist, SB gist, and RM brin. Sequence operations, RM sequence. Transaction operations, RM exact, RM multi-exact, RM clog, RM xlog, RM commit ts. Tablespace operations, RM smgr, RM dbase, RM tablespace, and RM relmap. Replication and hot standby operations, RM standby, RM REPL origin, RM generic ID, RM logical message ID. Here are some representative examples of how resource managers work in the following. If insert statement is issued, the header variables XLRMID and XLInfo of its Xlog record are set to RM heap and Xlog heap insert respectively. When recovering the database cluster, the RM heaps function heap Xlog insert selected according to XLInfo replays this Xlog record. Though it is similar for update statement, the header variable XLInfo of the Xlog record is set to Xlog heap update, and the RM heaps function heap Xlog update replays its record when the database recovers. When a transaction commits, the header variables XLRMID and XLInfo of its Xlog record are set to RM exact and to Xlog exact commit, respectively. When recovering the database cluster, the function exact redo commit replays this record. In version 9.5 or later, one variable, XL length, has been removed from the structure Xlog record to refine the Xlog record format, which reduced the size by a few bytes. Note: Xlog record structure in version 9.4 or earlier is defined in source include access xlog.h, and that of version 9.5 or later is defined in source include access xlog record.h. The heap xlog insert and heap xlog update are defined in source backend access heap am.c, while the function exact redo commit is defined in source backend access transam exact c. 9.4.2 Data portion of Xlog record, version 9.4 or earlier. Data portion of Xlog record is classified into either backup block, entire page, or non-backup block, different data by operation. The internal layouts of Xlog records are described below, using some specific examples. 9.4.2.1 Backup Block. A backup block is shown in figure 9.8a. It is composed of two data structures and one data object as shown below. The structure X log record, header portion, the structure BKP block, and third, the entire page apart from its free space. The BKP block contains the variables to identify this page in the database cluster, i.e., the rel file node and the fork number of the relation that contains this page, and this page's block number. The beginning position and the length of this page's free space. 9.4.2.2 Non-backup block. In non-backup blocks, the layout of data portion differs depending on each operation. Here, an insert statement's xlog record is explained as a representative example. See figure 9.8b. In this case, the xlog record of the insert statement is composed of two data structures and one data object as shown below. The structure xlog record, header portion, the structure xl heap insert, and the inserted tuple. To be precise, a few bytes is removed from the tuple. The structure xl heap insert contains the variables to identify the inserted tuple in the database cluster, i.e., the rel node of the table that contains this tuple, and this tuple's TID, and a visibility flag of this tuple. Note: the reason a few bytes from inserted tuple is described. The reason to remove a few bytes from the inserted tuple is described in the source code comment of the structure XL heap header. We don't store the whole fixed part, heap tuple header, of an inserted or updated tuple in WAL. We can save a few bytes by reconstructing the fields that are available elsewhere in the WAL record, or perhaps just plain not needn't be restructured. One more example to be shown here. See figure 9.8c. Xlog record of checkpoint. Xlog record and a checkpoint. The Xlog record of checkpoint record is quite simple. It is composed of two data structures as shown below. The structure Xlog record, the header portion, and the checkpoint structure, which contains its checkpoint information. Note: XL heap header structure is defined in source include access htup.h, while the checkpoint structure is defined in source include catalog pgcontrol.h. 9.4.3 Data portion of Xlog record, version 9.5 or later. In version 9.4 or earlier, there was no common format of Xlog record, so that each resource manager had to define one's own format. In such a case, it became increasingly difficult to maintain the source code and to implement new features related to WAL. In order to deal with this issue, a common structured format, which does not depend on resource managers, has been introduced in version 9.5. Data portion of Xlog record can be divided into two parts: header and data. See figure 9.9. Header part contains 0 or more Xlog record block headers, and 0 or 1 Xlog record data header short, or xlog record data header long. It must contain at least either one of those. When its record stores full page image, i.e. backup block, xlog record block header includes xlog record block image header, and also includes xlog record block compress header if its block is compressed. Data part is composed of 0 or more block data and 0 or 1 main data, which correspond to the xlog record block headers and to the xlog record data header, respectively. Note: WAL compression. In version 9.5 or later, full page images within xlog record can be compressed using LZ compression method by setting the parameter WAL compression enable. In that case, the structure xlog record block compress header will be added. This feature has 2 advantages and 1 disadvantage. The advantages are reducing I/O costs for writing records and suppressing the consumption of WAL segment files. The disadvantage is consuming much CPU resource to compress. 9.10 Examples of xlog records, version 9.5 or later. The backup block created by insert statement, as shown in 910A, is composed of 4 data structures and 1 data object, as shown below. The structure xlog record header portion, the structure xlog record block header, including 1 log record block image header, the structure xlog record data header short, a backup block, block data, the structure XL heap insert, main data. Xlog record block header contains the variables to identify the block in the database cluster, the rel file node, the fork number, and the block number. Xlog record image header contains the length of this block and offset number. These 2 header structures together can store same data of BKP block used until version 9.4. Xlog record data header short stores the length of XL heap insert structure, which is the main data of the record. See the note below. Note: the main data of xlog record, which contains full page image, is not used except in some special cases, e.g. being in logical decoding and speculative insertions. It's ignored when this record is replayed, which is the redundant data. It might be improved in the future. In addition, main data of backup block records depend on statements which create those. For example, update statement appends XL heap log or XL heap updated. 9.4.3.2 Non-backup block. Next, non-backup block record created by insert statement will be described as follows. See 910b. It is composed of 4 data structures and 1 data object, as shown below. The structure xlog record header portion, the structure xlog record block header, the structure xlog record data header short, an inserted tuple, to be exact, a XL heap header structure, and an inserted data entire, and finally the structure XL heap insert, the main data. Xlog record block header contains 3 values, the rel file node, the fork number, and the block number to specify the block inserted at the tuple and the length of the data portion of the inserted tuple. Xlog record data header short contains the length of new XL heap insert structure, which is the main data of this record. The new XL heap insert contains only 2 values. offset number of this tuple within the block, and visibility flags. It became very simple because xlog record block header stores most of the data contained in the old one. As the final example, a checkpoint record is shown in figure 910C. It is composed of 3 data structures: the xlog record header portion, the xlog record data header short structure contained of the main data length, and the structure checkpoint main data. Note: the structure XL heap header is defined in source include access htub.h, and checkpoint structure is defined in source include catalog pg control.h. Though the new format is a little complicated for us, it is well designed for the parser of the resource managers, and also size of many types of xlog records is usually smaller than the previous one. Size of main structures is shown in figures 9.8 and 910, so there you can calculate sizes of those records and compare each other. The size of new checkpoint is greater than the previous one, but it contains more variables. 9.5 Writing of xlog records. Having finished the warming up exercises, now we are ready for understanding the writing of xlog records. First, issue the following statement to explore the Postgres internals. Insert into table values A. By issuing the above statement, the internal function exect simple query is invoked. The pseudocode of exect simple query is shown below. In the following paragraphs, each line of pseudocode will be explained for understanding the writing of xlog records. Step 1. Write the state of this transaction in progress to the clog. Step 2. Insert a tuple, creates an xlog record, and invoke the function xloginsert. Write the xlog record of the inserted tuple to the WAL buffer and update pages pd_lsn. 4. Invoke commit action. 5. Or 4 still. Write a xlog record of this commit action to the WAL buffer. 5. Write and flush all xlog records on the WAL buffer to the WAL segment. And 6. Change the state of this transaction from in progress to complete to committed on the clog. The function xlogWrite writes and flushes all xlog records on the WAL buffer to the WAL segment file. If the parameter WALSync method is set to OpenSync or OpenDataSync, the records are synchronously written because the function writes all records with the open system call specified in the flag OSync or ODSync. If the parameter is set to fsync, fsync write through, or fdatasync, the respective system call fsync, fcntl, or with full fsync option, or fdatasync will be executed. In any case, all xlog records are ensured to be written into storage. In the above example, commit action has caused the writing of xlog records into the WAL segment. but such writing may be caused when any one of the following occurs. 1. One running transaction has been committed or aborted. 2. The WAL buffer has been filled up with many tuples having been written. The WAL buffer size is set to the parameter WAL buffers. Or 3. A WAL writer process writes periodically. See next section. If one of the above occurs, all WAL records on the WAL buffer are written into a WAL segment file, regardless of whether their transactions have been committed or not. It is taken for granted that DML operations write X log records, but so do non-DML operations. As described above, a commit action writes a Xlog record that contains the ID of the committed transaction. Another example may be a checkpoint action to write a Xlog record that contains general information of this checkpoint. Furthermore, select statement creates Xlog records in special cases, though it does not usually create them. For example, if deletion of unnecessary tuples and defragmentation of necessary tuples in pages occurs by heap-only tuple during a select statement processing, the Xlog records of modified pages are written into the WAL buffer. 9.6. WAL writer process. WAL writer is a background process to create the WAL buffer periodically and write all unwritten Xlog records into the WAL segments. The purpose of this process is to avoid burst of writing of Xlog records. If this process has not been enabled, the writing of Xlog records might have been bottlenecked when a large amount of data committed at one time. Default is 200 milliseconds. 9.7. Checkpoint processing in Postgres. In Postgres, the checkpointer, background process, performs checkpoints. Its process starts when one of the following occurs. The interval time set for checkpoint timeout from the previous checkpoint has gone over. The default is 300 seconds or 5 minutes. In version 9.4 or earlier, the number of WAL segment files set for checkpoint segments has been consumed since the previous checkpoint. The default number is 3. In version 9.5 or later, the total size of the WAL segment files in PG-Xlog, in version 10 or later PG-WAL, has exceeded the value of the parameter max WAL size. The default value is 1 gigabyte or 64 files. Postgres server stops in smart or fast mode. Its process also does it when a super user issues checkpoint command manually. Note, in version 9.1 or earlier, the background writer process did both checkpointing and dirty page writing. In the following subsections, an outline of checkpointing and PG control file is given, which holds the metadata of the current checkpoint. 9.7.1 Outline of the checkpoint processing. Checkpoint process has two aspects: the preparation of database recovery and the cleaning of dirty pages on the shared buffer pool. In this subsection, its internal processing will be described with focusing on the former one. See figure 9.13. 1. After a checkpoint process starts, the redo point is stored in memory. Redo point is the location to write the Xlog record at the moment when the latest checkpoint is started, and the starting point of database recovery. 2. A Xlog record of this checkpoint, i.e. checkpoint record, is written to the WAL buffer. The data portion of the record is defined by the structure checkpoint, which contains several variables such as the redo point stored in step 1. In addition, the location to write checkpoint record is literally called the checkpoint. 3. All data in shared memory, e.g. the contents of the clog, etc., are flushed to storage. 4. All dirty pages of the shared buffer pool are written and flushed into storage gradually. 5. The PG control file is updated. This file contains the fundamental information such as the location where the checkpoint record has written, aka checkpoint location. To summarize the description above from the viewpoint of the database recovery, checkpointing creates the checkpoint record, which contains the redo point and stores the checkpoint location and more into the PG control file. Therefore, Postgres enables to recover itself by replaying WAL data from the redo point obtained from the checkpoint record provided by the PG control file. 9.7.2 PG control file. As the PG control file contains the fundamental information of the checkpoint, it is certainly essential for database recovery. If it is broken or unreadable, the recovery process cannot start up in order to not obtain a starting point. Even though PG control file stores over 40 items, 3 items to be required in the next section are shown in the following. State. The state of database server at the time of the latest checkpointing starts. There are 7 total states. Startup is the state that the system is starting up. Shutdown is the state that the system is going down normally by the shutdown command. In production is the state that the system is running, and so on. Latest checkpoint location. The LSN location of the latest checkpoint record. Prior checkpoint location. LSN location of the prior checkpoint record. Note that it is deprecated in version 11, and the details are described in a note below. A PG file is stored in the global subdirectory under the base directory. Its contents can be shown using the PG control data utility. Removal of prior checkpoint in Postgres 11. Postgres 11 or later will only store the WAL segments, which contain the latest checkpoint or newer. The older segment files, which contain the prior checkpoint, will not be stored to reduce the disk space for saving WAL segments under the PG xlog PG WAL subdirectory. 9.8 Database recovery in Postgres. Postgres implements the redo log-based recovery feature. Should the database server crash, Postgres restores the database cluster by sequentially replaying the xlog records and the WAL segment files from the redo point. We had already talked about the database recovery several times up to this section, so I will describe 2 things regarding the recovery which we have not explained yet. The first thing is how Postgres begins the recovery process. When Postgres starts up, it reads the PG control file at first. The following are details of the recovery processing from that point. 1. Postgres reads all items of the PG control file when it starts. If the state item is in production, Postgres will go into recovery mode because it means the Postgres was not stopped normally. If shut down, it will go into normal startup mode. 2. Postgres reads the latest checkpoint record, which location is written in the PG control file, from the appropriate WAL segment file and gets the redo point from the record. If the latest checkpoint record is invalid, Postgres reads the one prior to it. If both records are unreadable, it gives up recovering itself by itself. Note that the prior checkpoint is not stored from Postgres 11 on. Then third, proper resource managers read and replay Xlog records in sequence from the redo point until they come to the last point of the latest WAL segment. When a Xlog record is replayed, and if it is a backup block, it will be overwritten on the corresponding table's page regardless of its LSN. Otherwise, a non-backup block's Xlog record will be replayed only if the LSN of this record is larger than the PD LSN of a corresponding page. The second point is about the comparison of LSNs. Why the non-backup block's LSN and the corresponding page's PD LSN should be compared. Unlike the previous examples, it's to be explained using a specific example emphasizing the need of comparison between both LSNs. One, Postgres inserts a tuple into table A, writes a Xlog record LSN 1. 2. The background writer process writes the table A's page into storage. At this point, the page's PD LSN is LSN 1. 3. Postgres inserts a new tuple. Postgres inserts a new tuple into table A and writes a Xlog record at LSN 2. The modified page is not written into storage yet. Unlike the examples in Overview, the table A's page has been once written into storage in this scenario. Do shut down with immediate mode and start. So here's the database recovery. 1. Postgres loads the first Xlog record and the table A's page, but does not replay it because the record's LSN is not larger than the table A's LSN. Both values are LSN 1. In fact, it is clear at a glance that there is no need to replay it. 2. Next, Postgres replays the second Xlog record because its record's LSN, LSN2, is larger than the current table A's LSN, LSN1. As can be seen from this example, if the replaying order of non-backup blocks is incorrect or non-backup blocks are replayed out more than once, the database cluster will no longer be consistent. In short, the replay operation of non-backup block is not idempotent. Therefore, to preserve the correct replaying order, non-backup block records should replay if and only if its LSN is greater than the corresponding page's PD LSN. On the other hand, as the redo operation of backup block is idempotent, backup blocks can be replayed any number of times regardless of its LSN. 9.9 WAL segment files management. Postgres writes Xlog records to one of the WAL segment files stored in the PG Xlog subdirectory, in version 10 or later, PG WAL subdirectory, and switches for a new one if the old one has been filled up. The number of the WAL files will vary depending on several configuration parameters, as well as server activity. In addition, their management policy has been improved in version 9.5. In the following subsections, switching and managing WAL segment files are described. 9.9.1 WAL segment switches. WAL segment switches occur when one of the following occurs. 1. WAL segment has been filled up. 2. the function pg switch xlog has been issued. Or 3, archive mode is enabled and the time set to archive timeout has been exceeded. Switched file is usually recycled, renamed, and reused for future use, but it may be removed later if not necessary. 9.9.2 WAL segment management in version 9.5 or later. Whenever the checkpoint starts, Postgres estimates and prepares the number of WAL segment files required for the next checkpoint cycle. Such estimate is made with regards to the numbers of files consumed in previous checkpoint cycles. They are counted from the segment that contains the prior redo point, and the value is to be between min WAL size, by default 80 megabytes, i.e. 5 files, and max WAL size, 1 gigabyte, i.e. 64 files. If a checkpoint starts, necessary files will be held or recycled, while the unnecessary ones removed. A specific example is shown in Figure 9.17. Assuming that there are 6 files before checkpoint starts, WAL 3 contains the prior redo point in version 10 or earlier, and in version 11 or earlier or later, the redo point. And Postgres estimates that 5 files are needed. In this case, WAL 1 will be renamed as WAL 7 for recycling, and WAL 2 will be removed. Note: the files older than the one that contains the prior redo point can be removed because, as is clear from the recovery mechanism described in section 9.8, they will never be used. If more files are required due to a spike in WAL activity, new files will be created while the total size of WAL files is less than max WAL size. For example, in Figure 9.18, if WAL 7 has been filled up, WAL 8 is newly created. The number of WAL files adaptively changes depending on server activity. If the amount of WAL data writing has constantly increased, the estimated number of the WAL segment files as well as the total size of WAL files also gradually increase. In the opposite case, i.e., the amount of WAL data writing has decreased, these decrease. If the total size of the WAL files exceeds max WAL size, a checkpoint will be started. Figure 9.19 illustrates this situation. By checkpointing, a new redo point will be created, and the last redo point will be the prior one, and then unnecessary old files will be recycled. In this way, Postgres will always hold just the WAL segment files needed for database recovery. The configuration parameter WAL keep segments and the replication slot feature also affect the number of WAL segment files. 9.9.3 WAL segment management in version 9.4 or earlier. The number of WAL segment files is mainly controlled by the following 3 parameters: checkpoint segments, checkpoint completion target, and WAL keep segments. Its number is normally more than 2 plus checkpoint completion target times checkpoint segments plus 1. Checkpoint segments plus WAL keep segments plus 1 files. This number could temporarily become up to 3 times checkpoint segments plus 1 files, depending on server activity. The replication slot also influences the number. As mentioned in section 9.7, checkpoint process occurs when the number of checkpoint segment files has been consumed. It is therefore guaranteed that 2 or more redo points are always included within the WAL files, because the number of files is always greater than 2 times checkpoint segments. The same is true if it occurs by timing out. Thus, Postgres will always hold enough WAL segment files, sometimes more than necessary, required for recovery. Note: in version 9.4 or earlier, the parameter checkpoint segments is a pain in the neck. It is set at a small number. Checkpoints occur frequently, which causes a decrease in performance. Whereas if set at a large number, the huge disk space is always required for the WAL files, some of which is not always necessary. In version 9.5, the management policy of WAL files has been improved and the checkpoint segments has obsoleted. Therefore, the trade-off problem described above has also been resolved. 9.10 Continuous archiving and archive logs. Continuous archiving is a feature that copies WAL segment files to an archival area at the time when WAL segment switches, and is performed by the archiver background process. The copied file is called an archive log. This feature is usually used for hot physical backup and point-in-time recovery. The path of archival area is set to the configuration parameter archive command. For example, using the following parameter, WAL segment files are copied to the directory home Postgres archives every time when each segment switches. Archive command. Where placeholder %p is the copied WAL segment, and %f is the archive log. When WAL segment file WAL7 is switched, the file is copied to archival area as archive log 7. The parameter archive command can be set to any Unix commands and tools. So if you can transfer the archive logs to other hosts by setting up the skip command or any file backup tools instead of ordinary copy command. Note: Postgres does not clean up created archiving logs. So you should properly manage the logs when using this feature. If you do nothing, the number of archiving logs continues to increase. The PG archive cleanup utility is one of the useful tools for archiving log management. Let's check out what remains. I think we've finished all of the long chapters. So all we have left are chapter 10 and chapter 11. Let's check out some scroll bars. It's not a terrible scroll bar. How about this one? Streaming replication. Also not terrible. Might do both of these at once. But that's all for today. Gotta do work stuff. Alright, see ya. I tried to change some of the microphone settings, but I think I can still hear myself breathe. I'll keep working on that. Alright, see ya.